Dear students, in last video, that is function analysis 3 video, we have discussed the proof of projection theorem. We have discussed this proof and in a detailed way we have proved it and explained everything about the projection theorem. And finally we completed the discussions with the definition of a bounded linear function on X. What's a bounded linear function? Let X be an inner product space over K and f a continuous linear function on x, then the x is m such that norm of fx less than or equal to m norm of x for all x in x. We call f is a bounded linear function on x. Today we are going to discuss a result which is analogous to the Bessel's inequality. That is, first we want to introduce a new definition. That's what a dual of x. What do you mean by a dual? Let x be an inner product space over K. The set x dash of all continuous linear functionals on x is called the dual of x. The set x dash of all continuous linear functionals on x is called the dual of x. Clearly x dash is a linear space, definitely, under pointwise addition and scalar multiplication. Moreover, norm is also defined. See, norm f, that is for f in x dash, norm f is equal to supreme of mod fx such that x in x and norm x less than or equal to 1. Then it is a norm on x dash. We can write a mod of fx less than or equal to norm of f in norm of x for f in x dash, x in x, which we are using in the next theorem. We can use that idea too. So we are coming to the result which is analogous to the Bessel's inequality, and is given in the lemma below, and its proof also we are going to complete in this section in today's class. There are two parts for this lemma, parts A and B. We are proving both today in this video. Okay, statement I can give: let x be an inner product space f in x dash. Part A, let u1, u2, etc. be an orthonormal set in x, then sigma modulus of fun square is less than or equal to norm f square. That is part A. And part B, let u alpha be an orthonormal set in x, and ef is collection or set u alpha such that fu alpha is different from 0. Then this collection ef is a countable set. You can say set u1, u2, etc. And how it is? If f is denumerable, then f of un converges to 0 as n tends to infinity. You can discuss this proof. What is given? Let x be an inner product space and f in x dash. Part A, we are coming to part A. Let u1, u2, etc. be an orthonormal set in x as given in the statement. And you take for m equal to 1 to etc. You can take ym as sigma n equal to 1 to m. F un bar un is an element of x. Now consider norm of ym square. What is ym? Norm of ym square inner product ym, and replace ym by this value. What is that? Ym is sigma n equal to 1 to m f un bar un. So you are replacing ym by that value, and you are rewriting the inner product. And from the first term you can take sigma n equal to 1 to m f un bar outside. Then left, what are you getting? Un is their balance in the inner product. And the second term f ui bar, that can be taken outside with its conjugate, in the sense k bar form. What is that? F ui bar bar. So you are getting f ui. So sigma n equal to 1 to m f un bar. Then other side, second term, already we have written the second term in terms of I equal to 1 to m. Just to show the difference, for n, first term n equal to 1 to m and the second term I equal to 1 to m. So that f ui bar bar is taken outside. So sigma n equal to 1 to m f un bar. Then sigma I equal to 1 to m f ui. Then inner product unui. So what is get? Sigma n equal to 1 to m f un bar. Then un only will exist. Inner product un. All others will be 0 because it's an orthonormal set. set u1, u2, etc. is an orthonormal set, and the inner product u and ui equals 0 for I not equal to n. So you are having sigma n equal 1 to m f un bar f un, inner product un, that is norm un square, and we know it's an orthonormal set in the sense norm un is 1. So sigma n equal to 1 to m f un bar into f un, that is what sigma n equal to 1 to m mod f un square, equal it as result 1. Now consider f of ym. What is f of ym? Ym is like this, sigma n equal to 1 to m f un bar un, and the f of ym, it's a linear function. Of course f is an element of x star, so you can take sigma n equal to 1 to m f un bar into then un, that is f of un comes. Is equal to sigma n equal to 1 to m mod f un square, you call it as beta m, and call it as result 2 for m equal to 1 to etc. For beta m is f of ym, which is less than or equal to modulus f of ym, which is less than or equal to norm f into norm of ym for all m equal to 1 to etc. Reason f is in x dash and ym in x. Just refer the previous idea what is written there. Is equal to norm of f into norm of ym. You can write root of beta. Why? Because from 1 and 2, beta m is norm of ym square, or norm of ym is root beta m. Thus beta m is less than or equal to norm f into root of beta m squaring beta m square less than or equal to norm f square into beta m, or beta m less than or equal to norm f square for all m equal to 1 to etc. Replace beta m with sigma n equal to 1 to m f un square mod f un square less than or equal to norm f square. This implies limit n tending to infinity, because sigma n equal to 1 to m I take. So limit n tending to infinity, sigma n equal to 1 to m mod f n square less than or equal to norm f square. This implies sigma n equal to 1 to infinity, right? Mod f n square less than or equal to norm f square. That's what the proof of part A. Now coming to part B. Yes, we can start with let us set u alpha be an orthonormal set in X, and EF you are taking, that is collection u alpha such that f u alpha not equal to 0. If f is equal to 0, then there is nothing to prove directly. If f is not equal to 0, we can discuss as follows. For j equal to 1 to etc., you write Ej. What is Ej? Collection u alpha such that norm f less than or equal to j into modulus f for u alpha, you write like that. Fix this j. Fix j so that Ej contains distinct elements u alpha 1, u alpha 2, etc., u alpha m. You are supposing that Ej contains distinct elements u alpha 1, u alpha 2, etc., u alpha m. Then we have norm f less than or equal to, just refer Ej definition, j modulus of f u alpha I, you write. I varies from 1 to m. So norm f square less than or equal to, on squaring, j square mod f u alpha I square for I equal to 1 to m. Then taking the summation m times. So what are you getting? M norm f square is less than or equal to j square sigma I equal to 1 to m modulus of f u alpha I square, which is less than or equal to j square into norm of f square, because part A, what are you getting? Sigma n modulus of f un square less than or equal to norm f square, that you are replacing here. So ultimately you are getting m norm f square less than or equal to j square norm f square, or m is less than or equal to j square. What is the meaning? Ej contains at most j square elements. But what is EF? EF is union of Ej's. That is, j varies from 1 to infinity. This implies EF is countable. Clear ആയില്ലേ apart? Then EF is denumerable. If EF is denumerable, you take EF equal to set E1, U2, etc. Then we have sigma n equal to 1 to infinity modulus f un square less than or equal to norm f square, which is less than infinity. Since mod f un square is the nth term of a convergent series of non-negative real numbers. This implies mod fun square is converging to 0 as n tends to infinity, or mod fun is converging to 0 as n tends to infinity, or fun is converging to 0 as n tends to infinity. ഇതാണ് നമ്മുടെ ആ പ്രൂഫ് അവിടെ നമ്മുടെ കംപ്ലീറ്റ് ചെയ്യണം. ദാറ്റ്സ് ഓൾ അബൌട്ട് ദി പ്രൂഫ് ഓഫ് ദിസ് പാർട്ട്. സോ we get two parts, that is A and B, both we have proved here.